Good morning, everyone. Let's start the morning session. The first speaker is Jeehoon Park. His title is Cassels-Tate pairing and arithmetic UF and sharing for lemma groups. We'll start.
Good introduction. And I also would like to thank the organizers for invitation to this nice workshop. And I'm gonna talk about the Cassels-Tate pairing and the corresponding arithmetic DF theory for English. So let me start. Let me just briefly say something about the physics. So actually, I'm doing some sort of a physical mathematics, right? Not of mathematical physics. So the physics leads a way to study certain structures of mathematics. So what kind of structures we can expect from physics, like quantum field theory? So the input of d-dimensional QFT is basically three things: space-time, a d-dimensional manifold M, and there is a field, like space of fields. And basically, it's a function space on M, sections over 5 measure of d mu, and there is an action function. That's the sort of input data of QFT. Once you have such input data, the output of this QFT is the so-called diffusion function. It's an important invariant in physics. And also, more generally, there's correlation functions using these observables. So that's the sort of physical structure, mathematical structure coming from the physics. So, and among quantum field theory, so if you forget the metric on a manifold, then you can think of topological quantum field theory. So, and topological quantum field theory can be studied, the data was this, but can be studied mathematically using extended way. The sort of like functors and two functors and three functors, things like that. So for example, three-dimensional extended topological quantum field theory means this kind of functor. So there is a closed three manifold, then you will get a certain number. And there's a Bordism category, like close to manifold, then you associate a certain Hilbert space. And there's a Bordism, like between two manifolds, like diffeomorphism class of oriented manifold X with boundary at Y bar, Y1 bar, and Y2. Then this X is called Bordism. Then you get a C linear map from the vector spaces attached on the boundary, those two manifolds. And then there is a further things like this two morphisms and one morphisms. These are, I think it's very successful. Another structure is that this functor should respect the monoidal structures. So disjoint union on the left-hand side should go to a tensor product on the category of vector spaces. And for example, like the empty two manifold, like closed two manifold, gets into the monoidal unit, like C of vector space, category of vector spaces. So there is a Bordism, like from empty two manifold to closed two manifold Y corresponds to a linear map, right, from this under this functor, linear map from C to the vector space Z of Y, which is equivalent to giving just one vector in this Hilbert space Z of Y. So this is kind of data. So arithmetic TQFT will do the same analog based on arithmetic topology. So instead of like this closed three manifold and two manifolds, we'll use the spectrum of ring of integers and also spectrum of ring of integers and invert primes and things like that. So here's the three-dimensional sort of extended arithmetic TQFT based on arithmetic topology. So arithmetic topology is the sort of main theme of this conference. So I somehow assume people know the dictionary between the analogy between knots and primes. And so if you assume that, then we just write down the axioms exactly like the usual TQFT in the case of arithmetic setting. So I summarize what it is. Like say, F is a number field. For simplest technical reason, I will assume it's a totally imaginary, and it's a ring of integers or F. And there's a certain finite set of places of F, is S, and And at P will be the p-adic completion of F, and P is the prime ideal of F. That's the decision. And then I like to construct functor from the Buddhism category of this thing. Like say close to manifolds corresponds to spec of local field at P. In particular, we are looking at the Étale side. We will look at the Étale cohomology and the Étale cohomological dimension of spec at P, which is just the Galois cohomology too. So it's like close to many. And if you look at the spectrum of OF, invert the primes in S, then it's like a three manifold, Étale cohomological dimension 3, and whose boundaries are these close to manifolds and primes P in S. Okay? So that's the thing. Then what you have to do, you have to associate vector space to spec FP, and then you have to associate C linear map between these vector spaces attached to spec OF bracket 1 over S. Of course, I mean, depending on theory, there, many kind of theory can exist. And the first example, I think, it's given by Min-Young Kim, and Min-Young Kim proposed or initiated this arithmetic gauge theory business, and he proposed to, he gave an example of this sort of arithmetic TQFT which is an analog of Chern-Simon theory. So that's arithmetic Chern-Simon theory. And then the collaborators, I mean, including me, try to compute the arithmetic Chern-Simons invariant in particular examples. And that's the Chern-Simon theory 2. And then Min-Young gave a more like physical interpretation of this arithmetic TQFT. And then later, like other works. Yeah. So we connected the linking numbers. So we defined the arithmetic linking numbers and then relate this arithmetic Chern-Simon theory. And then also Hiraku and Junyoung and Morishita, they more formally developed this arithmetic Chern-Simon theory with the finite gauge group. And after this, this is the first example, arithmetic Chern-Simon theory, which I didn't explain, but there is a certain like arithmetic TQFT called arithmetic Chern-Simon theory or arithmetic digraph-Witten theory. I mean, I think the reason why Min-Young called arithmetic Chern-Simon theory is that at the time, he was thinking of include the p-adic Lie group too as a gauge group. But in fact, the computation we gave is only for finite groups. And then Chern-Simon theory with the finite gauge group is usually called digraph-Witten theory. So that's the name, arithmetic digraph-Witten theory. And then the basic idea was the partition function of this arithmetic Chern-Simon theory, arithmetic TQFT, should be related to the L functions in number theory. That was the motto, I think. And then we tried to compute invariants like partition functions in arithmetic Chern-Simon theory, but couldn't find a very nice connection to L functions. And then later, the Carson and Min-Young came, and they realized that BF theories might be better for a connection to the L functions in number theory. So they derived a certain formula in arithmetic BF theory and connect this to Shah groups and Tay-Shafarevich groups and class groups and things like that. So that's the reason why we need another like arithmetic BF theory, arithmetic TQFT. And then based on this arithmetic BF theory, we were able to actually connect the path integral to the Kubota-Leopold p-adic L functions. Certain connections. It was not complete, but there are, actual connections there. So I think people know basically what Chern-Simon theory is and what is BF theory. And here's a very basic view of the origination of the name BF. And you see, BF is just letters. I mean, they could call AB theory because it's variables and A and B. So it's so G is a finite dimensional Lie algebra for simplicity, corresponding to Lie group G, and M is a closed-oriented D-manifold. Then the BF theory is defined by this action function. So you remember at the beginning in physics, the input of the QFT is, space-time, fields, and action functional. So this is the action functional. And how is it defined? So connection A in the trivial principal G bundle, i.e. it's like omega-1 m G. And there is a D minus 2 differential form with values in G star. And then you take the curvature. So they use usually F, in order to denote the connection. So it's FA. And then there's a natural pairing, right? So you get omega D, and then you can integrate over the whole M. Then you get a scalar, right? That's the sort of action functional. And because of that, notation PFA, they call it the PF theory. So now, what is arithmetic PF theory? We have to find the analog of that omega-1 mg, like also the omega d minus 2 stuff, right? But I'll do that when d equals 3, in 3-dimensional theory. So it's like omega-1 mg, omega-1 mg star. So that's the sort of the space of fields on this. Okay, so here's a basic notations for arithmetic PF theory. It's a preparation. So it's usual notation. F is a totally imaginary number field, and GF is absolute Galois group, and then corresponding local field, and then you fix the embedding of Galois group. And the YP is a spec FP. That's a closed 2-dimensional thing with invariant map. So invariant map gives actually orientation of spec FP. So invariant map, local invariant map is the isomorphism from H2 CP FP bar star to Q mod C. And then YP bar is simply just take the minus sign of the invariant. And CIGM is the group of inhomogeneous group cochains, and Zi cocycle, BI co-boundary, and cohomology. And there's also restriction map, just like localization map. Okay, that's the basic notations. And you see, I mean, my goal was, by the way, why I'm interested in this and start to work on this is, so after this observation that the PF theory is somehow more important than Chern-Simon theory, and it was more or less clear to the experts that Cassels-Tate pairing has a very similar flavor to this arithmetic PF functional. It was, if you look at the formula closely, they was kind of obvious. And then I encountered a paper. It's called Cassels-Tate theorem for finite Galois Marshalls, due to one of the organizers, Adams and Smith. And then I just read them, and then I just realized that this is a PF invariant. So I decided to do some naive exercise. I just formally developed arithmetic or TQFT, like PF theory, and then interpret that Cassels-Tate pairing in terms of that PF theory. So in other words, I'm just giving physical context to the Cassels-Tate pairing. And once you do that, then you can do something, right? And which usually mathematicians don't consider, like partition functions. So without this physical structures, like QFT structure, people wouldn't be able to consider like partition functions associated to BF, like associated to Cassels-Tate pairing, for example. And also I computed, you will see that the sort of entanglement entropy in this case of arithmetic PF theory. So let me start more technical thing. So it's Adam Morgan, Alexander Smith. That's the give me like all technical backgrounds which is needed to develop this theory. So I'll start from an exact sequence. So finite. This is, by the way, finite theory. Finite abelian like group, like discrete GF module. The Galois group acts on a finite things, and then I assume I have an exact sequence. So in physical theory, M1 is usually equal to M2. In physics, in physical PF theory, you remember that there's a G, Lie algebra G and a G star, right? So here, M1 and M2 are sort of plays a role of that. So, but why not? We can do slightly more general. So I use this general setting. So there is a input data is this discrete GF module, and then there's a local conditions. The local conditions are like W. It's a product of WV, and then I fix a finite set S, and outside S is unrarified conditions, and inside S you can give any conditions, like periodic Hart theory condition if you want, and or you can give no conditions, like you can take all the local cohomology group, or you can take the zero. There is a flexibility. And omega W1 and W2 are defined by the iota inverse of W pi of W. So that's the input data. So assume you have such a thing, then the theory is developed. So I think the easiest example is just the G mod P square in the middle and G mod P, and then kernel G mod P. That's the simplest example. And then Galois group acts on trivially. And when F includes like roots of unity, P power roots of unity, then that's the one example. Another example is the, say, William variety. You look at the P to the 2n torsion in the middle, and the P to the n torsion in the kernel, and the quotient is also P to the n. So that's the, I think it's two most typical examples of this kind of example. And number theorists well know that the Selmer group is important. The Selmer group is the first global Galois cohomology group whose local conditions are given by this W. So kernel of that, so which means you localize it, then you'll end up in W. So these local conditions. That's the Selmer group. And this Selmer group will be my space of fields of arithmetic BF theory. See, in the original theory, the space of fields is omega 1 mg times omega 1 mg star, right? So in this case, you will see here, let me show you again, the Selmer M2 W2, Selmer M1 check W1 per, this will be the equation of motion space, the space of fields. Okay, so now there's an important ingredient to develop the theory. That's the local Tate duality. I mean, this local Tate duality appears several times in this conference. So local cohomology group has cohomological dimension 2. There's a perfect pairing. And then for the theory, I need a notation for the cocycles, not just cohomology groups. So I just introduced the Z1W and Z1W such that you mod up by the boundary, then you will get omega 2 and omega 1, W2 and W1. See, that's the notation. So let's try to construct arithmetic BF theory. So the first thing I have to do is, like, given spectrum of FP, like two-dimensional stuff, I have to associate Hilbert space, right? Then how can you associate Hilbert space? And the usual way of doing that is that you have to construct a line bundle over a space of fields. You have to first construct a line bundle. And that's the key part. So here the line bundle will come from Q mod Z torsor. Once you construct the Q mod Z torsor of space of fields, then you can easily associate to line bundle. So let's do that. I think let me do that. Like I introduced notation tau v because rho v prime is an element in FV. So rho v is the Z1 GV M2, and rho v prime is GV M1 check. M1 check, it's a dual, Kummer dual.
Can I ask a question? When you set up the action functional, you didn't mention any line bundle. Can you just say how it comes?
What is the question?
When you define the action functional,
yeah, there is no line bundle. Right.
So
That's the quantization process. That's the classical theory. That's the classical theory, and then physicists want to quantize it, and then the process of quantization involves constructing line bundle, and then take dissection from that. So that's the kind of problem.
Line bundle on the moduli space.
Yeah, on the space of fields in this. In this case, that will be FV. Yeah. So it's a d-dimensional theory then D-1 manifold, then look at the functions on D-1 manifold, and over that space, you will construct a line bundle. And then take a section, then you will get a Hilbert space. Yeah. Or there's a polarization process, by the way. But in here, I'm really looking at the discrete space. Everything is a finite abelian group. So I will forget the polarization business, the Lagrangian business. Even though there is a Lagrangian here, even though this is discrete, like we saw that like the global, coming from the global cohomology class, that is a Lagrangian with respect to the state local pairing. But we can do both. I mean, we can use those Lagrangians and then take the sections over the Lagrangian. That's also will become a like Hilbert space. Anyways, yeah, let's start. So let's start from FV. So in order to construct the line bundle, I have to construct a fiber. So given a point in the base, that's the rho v, rho v prime. I choose a section. So all constructions at the beginning depends on a section of this exact sequence. Good. Section to pi. So I choose a section. And then you apply the inhomogeneous differential in group coordinates. And then you see that's actually belongs to the kernel of pi, which is the image of I. So you can take the I inverse. And that will be the element in Z2. This is exactly just, Box-time map. You have an exact sequence, and then there's a long exact sequence, right? And then this is how to construct that Box-time map. But I'm just, giving you everything in the chain level. Then you take the cup product with rho v prime, because rho v prime at the beginning was M1 dual, right? So this one has iota inverse ds rho v has value in M1, but rho v prime is M1 check, so you can take the cup product. Then you will end up with G3 Gv FV star, right? Then we use the fact that cohomological dimension of Gv is 2. So note that it's two-dimensional stuff. So you can take the inverse image of this I inverse ds rho cup product of V prime, and then take the modulo, not G2. This is typo. Sorry, it's B2. The boundary of Gv FV star. Then you see, I mean, this becomes a Q mod Z torsor via the local invariant map. Because you take the inverse image in element in B. That's the key construction. Given a tau V, and then you construct the Q mod Z torsor through the invariant map. Now, I just study how this thing behaves under the choice of the section S, and how does it behave on a cohomology class of tau V, rho V and rho V prime. And this is a simple computation. And you sort of need a projective limit construction, right? And then you show that projective limit exists, and the answer gives us a Q mod, non-trivial Q mod Z torsor. So if I just compute these things, say CV is the category and whose objects are co-cycles, and the morphisms are given by co-boundaries, then the assignments I just gave, given tau V, LV as tau V, that Q mod Z torsor, then it satisfies this condition. So it is a little complication here, and if you compute this behavior of the map, there's this kind of thing. And also you can check how this construction behaves under the choice of the section S. And in this case, it's a lot easier. I mean, this SNS prime. And then you can show that this SV, the category of object whose objects are sections to pi and morphisms between two sections are given by these elements alpha m. Then this is a connected groupoid, and this functor has no holonomy. I mean, the given automorphism, the corresponding thing has only identity map. Then you can take the projective limit with respect to index category, the SV. Then that actually exists, and it's actually Q mod Z. So I'll do that. So this is so-called invariant section construction. It's a projective limit construction, so-called. So LV as tau V is the space of invariant sections of the functor. And then you can also think of the invariant section of the functor on the cohomology class, then here's a little subtlety here. If you use the full H2 H1 GV, and you won't get a non-trivial Q-mod-Z toaster. But if you restrict to the Selmer local conditions, then I can show that it has no holonomy, and then it has the Q-mod-Z toaster things. So that's the proposition. We're starting from the local Galois cohomology class, pair of Galois cohomology class, that LV tau V is the Q-mod-Z toaster via the local map. And in consequence, I mean, we constructed Q-mod-Z toaster over this discrete space. You don't have to worry about the topology. It's just finite, set.
Is it? There is no scheme structure on that finite set?
I'm just looking at this only just finite, as a just discrete space, because I'm looking at the finite abelian group. So
you can put a scheme structure on it.
Yeah.
I mean, sorry, which characteristic? Where are we?
at P, like not. It doesn't have to be, but usually it's just a finite abelian group. So its size has a finite.
It's easy to put an FP scheme structure on the.
Yeah. I mean, true. Yeah. But I don't see that how
Because normally you would expect, especially if it's not co-prime to the characteristic, you would expect nilpotence and non-trivial derived structure, and then you actually need to write the action on the section of the line bundle to be given by differential operators, which will be non-trivial in those directions.
Well, I think eventually it may be important to consider.
Yeah.
They're kind of a preliminary.
Okay, yeah. I'll discuss this later. Right. So this is a summary. So we have this Q-mod-Z toaster of FV W bar, and then you can do this construction with respect to the finite set of primes, like in T. So using the sum of the local invariance map. As you can do the similar construction, and then you have a toaster over FT W bar. Then the simple proposition is that the additivity, the LV be the line bundle, associated with the Q-mod-Z toaster. Then this construction gives the tensor product of local component. That's you can check that. So this is the part of the axioms of TQFT, right? The disjoint union goes to tensor product, and this will be responsible for that. Okay, now I'm looking at the three-dimensional thing, global three-dimensional thing. Then XS is the spectrum of OF invert S and calcite, and there's an invariant map with the compact support cohomology. And Selmer group. So here I also consider the cochain co-cycle level. That's the Z1 cell and Z1 cell GF M1 check. And that's the FXS. And I use the notation bar FXSS as a Selmer group. That's the spatial fields on XS. Now, what you have to do is we have to construct arithmetic functional which belongs to that toaster, right? Boundary toasters, like on S, there was a toaster, and we have to construct that. So the construction is really the similar. I mean, we use the vanishing of this global Galois cohomology group H3GF F bar star is 0 for any prime number L primary subgroup is 0. So given this global element, like Selmer element in the Selmer group, you can find a two cochain such that D of that is iota inverse ds rho xs rho x prime theta. See, this is like exactly same as the local construction. You choose the section and take the derivative. and then take coproduct with rho prime. Then you just define it as a cohomology class, mod B2. And that actually belongs to the fiber over the boundary stuff, tau S. Tau S is like tau V is in S. Right. And then you can take the projective limit, and actually these are invariant sections. You can check that these are invariant sections. And this invariant section actually doesn't depend on a choice of this modulo B2 of GF F bar star. And in fact, it's a element in the pullback process. So this is the two-dimensional, coming from two-dimensional thing, and it's a restriction map, and then you take a pullback, then BFS is the section of that pullback line, pullback torsion. Okay, now, I mean, how can I relate this to the Cassels-Tate pairing? Cassels-Tate pairing is a number, right? But in here, arithmetic BF function is not a number. It's actually in the fiber, right, of the line bundle. But in fact, this line bundle is trivial, so over discrete space. So once you can choose a section, then using that section, we can make the trivialization explicit, and then this arithmetic BF functional will be a number. Right? So I'll do that. So choose any section of that line bundle, YT. Right? Then, okay, I just wrote down, you know, once you choose a section, then this phi YT gives explicit trivialization of the line bundle. So it's a line bundle, and this is a trivial line bundle, and there's an isomorphism there. And this isomorphism is given by that, you know, invariant map. Alpha B itself is not a cocycle, but if you
Make one comment. Yeah, sorry to interrupt, but I don't remember exactly, but this discussion of making the trivializations very explicit and dependence and so forth. I guess this was written down very clearly by Professor Morishita.
yeah, exactly. Yeah. At the beginning I mentioned, you know, this paper right here. The on arithmetic Daiga-Bruton theory. I was actually influenced by that article when I wrote down this.
I mean, from a physics point of view, it's kind of boundary conditions, but they made it very clear.
Yeah, that's right. So there was a starting point of this project. I mean, I just look at the Cassels-Tate pairing, and I thought that if I choose a right section, then that will be the arithmetic BF function will be the Cassels-Tate pairing. That was the original sort of idea, and so that's the YV, and then you can, you know, define arithmetic BF functional as a number. I mean, using that section, right? So I introduced the set of primes P, then arithmetic BF functional with respect to YT, the section YT, then that is simply just invariant B and restriction of that global 3 arithmetic BF functional minus that section. So each thing is not a cocycle. So if you take the difference, then it will become a cocycle. Then it makes sense to take the invariant map. Right. And there are many choices of sections, right? But the Cassels-Tate pairing uses very particular choice. I think that's important. And here is the that section. I call it YV Cassels-Tate. That's the section of this line bundle. So you see, let me recall. I mean, in order to explain that, I have to recall that Cassels-Tate pairing. So Cassels-Tate pairing is the bilinear pairing. The Selmer M2, you know, W2, Selmer M1 check, W1 per Q Z. And if I recall, I mean, how it was constructed, and you can write it down in this way. So all right. So given rho XS and rho X prime, so rho XS is in Selmer, and rho x prime is that Selmer. And then you choose a section S and restricted FV. Then this rho VM exists because of that exact sequence. You have an exact sequence. That exact sequence guarantees the existence of the lifting of that. So that's how I wrote down. Rho V pi, rho VM is this. Then you take the difference. Then you can check that this is actually a section of that line. That's the construction. Then the proposition is the Cassels-Tate pairing on the right-hand side is a BF functional with respect to that particular section, YS tilde CT. And the proof is just writing down the formula, then you will see it matches with each other. Okay. And another nice thing about this section, YS tilde CT, I mean, this actually doesn't depend on the choices of S and beta and rho VM. I mean, it's nice. It's not just a random section. It's a very nice sort of section. This YVCT. And this is why, I mean, mathematicians already use such a section in the business. Okay, here's another comment on orientation. I mean, if you develop the theory, then the orientation business can be incorporated in this arithmetic BF theory. Now, let me think about the quantization. We're almost there, right? We have a Q Z torser, so associated line bundle. So we can make the inner product space. In this case, it's a finite dimensional inner product space. Taking global sections. So close to manifold YV, so spec of FV, the geo YV will be, by definition, this sections of the line bundle. This is a finite dimensional like C vector space, and then you can put a natural Hermitian inner product structures using the section, for example. If you choose a section, then you have a trivialization, then section will be really the function, C-valued functions, right? And C-valued functions has a natural inner product. And then you can check the compatibility. I mean, depending on the choice of sections, it really doesn't depend on the choice of sections of the line bundle. That's the construction. And then this disjoint union, you take the section of that, then you will get a tensor product. So multiplicativity holds. And then you choose the orientation, then you will get a Hilbert space with the conjugated inner product space. That's just a notation. ZYV bar means Z of YV with the conjugated inner product. And then finally, I mean, the most important thing is that this path integral, this partition function. So we'll see, we'll define following the procedure of QFT, this Z X of S. And that will be the element of this boundary Hilbert spaces. And the orientation also works here. Here's a definition. I just wrote down explicitly how to construct the line bundle out of the Q Z tensor. So this is a little awkward notation, linearization, LINS. So Q Z torsors, and there's a corresponding line bundles. So essentially, you have an element in Q Z, then you will take the e to the 2 pi I, that element Q Z. So it's well-defined modulo Q. Right? So it's sort of unitary line bundle. And this slide is for depending on a different choice of sections. I mean, you can make the order diagram commute using this theta YV prime. So, and HS, as I mentioned, it's a section of that line bundle, and just Roman S will be the line bundle of the trivialized line bundle. So this can be realized as a C-valued functions. That's the difference. But in here, this theory is the abelian BF theory, by the way. We have a M and M1 and M2, right? M is an abelian group. So it's actually corresponds to the abelian BF theory. So in abelian case, the HS really doesn't depend on the section. If you look at the arithmetic diagram of this paper, and this Hilbert space actually depend on a choice of sections because of non-trivial action of the non-abelian group. In this case, it doesn't happen. So that's another nice thing. I mean, we can think about partition sort of functions in HS. So here's a definition. I mean, you see, this is a just usual definition. ZXS will be the sum of all the arithmetic BF functions with the boundary condition tau v. So tau v is a local thing, and then you look at the global thing whose boundary conditions are given tau v, right? Then you take the sum. That's the usual partition function business. Then you see that's actually in HS. So remember, HS is a line bundle. Given tau v's, then you will attach the element in the fiber. And if you introduce a section, then this will be just a function from FSW bar. So then it has a nice form, e⁻² pi I BFXS YS tilde tau XS. So this is the remember this will become Cassels-Tate pairing if you use the YS tilde CT. If you use a particular section, Cassels-Tate section, then that will be the Cassels-Tate pairing. So this physical QFT introduces like lead us to compute sum of e to the 2 pi I Cassels-Tate pairing over all Selmer groups. Right? So that's the invariant.
So can you say again what tau v is?
Small tau v.
Yeah.
Tau v is a rho v comma rho v prime. Rho v is the H1 GV M2.
Right.
And rho v prime is H1 GV M1 check. It's a pair. I mean, it's just matter of notation.
And this residue, this res v map,
Yeah, it's a restriction map.
restriction map.
Yeah. Tau XS is the global thing, and then you restrict it, your tau v is the local thing. Okay. Yeah, that's the notation. Yeah. You see, it's really all about notation. If you write down the notation carefully, then things become easier. Yeah, you see that. I mean, when I say tau sub s, that's a local thing. But tau XS, that's a global. Right. And then also I mentioned the gluing formula here. So I only have 5 minutes, so I'll have to catch up. So there's an S, but outside S is unramified conditions, right? But unramified things are more or less easier. So your unramified case, it's actually, Galois cohomology finite field, right? But finite field has homologous dimension 1, so you can also take the trivialization there. So that's the this one. It's H3 GV tilde. Even H2 is 0. H3 is 0. So even H2 equals 0. So you can choose a cochain which is sort of independent, and you can do this kind of construction. Exactly similar construction, and unramified BF invariant, and you can think about unramified BF zeta functions. Not zeta function, sorry. I'm number theorist. I'm so familiar with zeta function. It's a partition function. Then gluing formula. I think this is the most important axiom in QFT. And you're adding S prime, right, to S, and then you do some surgery, right? And S prime, positive orientation, negative orientation. And this is how it is behaved. S tilde, S prime bar, negative orientation. And there was an isomorphism, right? The theta S and S prime. And this line bundle is this tensor with the S prime. And then this part and bar part using the Hermitian inner product, like trace, and you can get LS tau S.
Excuse me. So I think about this. I mean, each prime in S is a boundary component.
Yeah.
So I'm thinking about this as how I'm a little bit like. So you have a bigger S that contains two different S's.
Yeah, S is there, and then you choose S prime, which is disjoint from S, and you make it a larger. So the goal is we want to compute the the BF functional with respect to S, right? The goal of the gluing formula is that you enlarge the prime, and then you compute the BF functional with the enlarged prime, and then minus this local ununified thing. So sort of not minus, it's like tensor.
But is this attaching along boundary components of two?
Yes, basically, I mean, attaching you take out the boundary condition, and then you're adding the boundary condition again with the different orientation.
You're attaching the cap.
Yeah.
Removing the prime from S.
Oh, okay.
Same as a cap.
Right, yeah. So then, I mean, you can actually show that this BF functional goes to the BF functional on S. Yeah, this is the classical part, and you can do the quantum part too.
Oh, sorry, it's not a cap. I guess it was a solid tool.
It's three-dimensional and two-dimensional, so
Yeah.
it's a solid torus. I mean, but two-dimensional, one-dimensional, it's capped. So this is a three-dimensional theory, so the analog will be solid torus. I mean, adding solid torus and then take out solid torus and then put it back. And there's a gluing formula for partition functions too. It's the same setup. I mean, you can set up the trace map, and then the partition function of XS can be computed with the partition functions of the bigger boundary with the ununified stuff. And this gluing formula is actually very helpful. I mean, you compute certain things in arithmetic TQFT business. Now, let me mention the partition function formula. So this formula says this is why BF theory is more connected to the L functions of number theory. See, if you compute this partition function over all Selmer elements with this Cassels-Tate BF functional, then you will simply get pi of Selmer group, size of pi of Selmer group times size of Selmer M1 check W1 bar. I mean, this results based on the Adam Morgan's results. I mean, they analyzed the left kernel of the Cassels-Tate pairing. And if you know the left kernel and right kernel of this Cassels-Tate pairing, then it's a simple character sum argument. So you use the character sum argument, you get this nice formula. So this means, Selmer group, if you have a elliptic curve business, the Selmer group will be the model size of the model V times, Tate Shafarevich groups. So,
is pi projection to the stack?
yeah, projection. Pi was the exact sequence. M1 and M2. Pi was the projection.
The M1 or M2?
M2.
M2.
Oh, M.
M2 is
Pi is M, right? Pi was M to M2 was the pi.
Yeah.
So this first part is M2 business, and second part is M1 check business. It's M2 and M1. So I think I can compare, this formula with the Carson Kim's formula. Now, I think I have 1 minute, so I'm screwed up a little bit. But here, this is sort of new invariant to mathematicians, I guess. Without physics, people would never consider it. And Min-Young suggested to compute the entanglement entropy in the arithmetic Chern-Simon theory. So what is entanglement entropy? Mathematically, it's very easy. You have a S, and there's a decomposition S1 and S2, I choose. And then the theory gives us a Hilbert space associated to the S, and which is the tensor product of HS1, tensor HS2, right? And then theory gives a vector in there. That's the partition function. And then the question is, this is a pure vector or not? In other words, it's just a V tensor W. It has a form of V tensor W. It's like pure, or it has a combination of vectors, linear combination of product of vectors. And there is a invariant which measures that stuff, whether the vector is pure or not. That's the von Neumann entanglement entropy. Right? So here's a brief formula of the von Neumann entanglement entropy. That is basically you have a state in product of two Hilbert spaces, and then think about the projection operator with that pure state. then using this isomorphism, you can think about the trace map. And there is also, partial trace map with respect to HB. And from there, you can think about density matrix. And then you use this trace of log density matrix. That's the entanglement entropy. And entanglement entropy is 0, then it becomes a pure vector, like just product, tensor product, 2 vectors. Otherwise, it's bigger, then it's more entangled, like 2 states in and more entangled. So I tried to compute this, and then first I gave a general formula, just following the definition. So it's this general formula, but this is not that helpful. I really just unraveled the definitions. And then if you really try to compute this in a particular example, it's not that easy. It's actually very difficult, but I was able to compute just one case, and that's the easiest case. But this case is somehow not interesting as I thought. Yeah. So the easiest example would be just G mod P square and pi and G mod P and local conditions. W1 is the whole thing, 3 in S, and W2 same, because that condition I inverse local condition is here. Iota inverse local condition should be local condition for G mod PG, and the pi of local condition gotta be the local condition for the quotient. And then you take the orthogonal complement, there will be 0 and blah, blah, blah. And then in this case, if you compute the entanglement entropy, then it turns out that in this case, BF functional becomes trivial. It's actually 0. You can show it's 0. So that means e to the 2 pi I Cassels-Tate pairing 0. So it's just 1. So this is really computing certain matrix computation with matrix computation of matrices like 1 blah blah 0 0 1 blah 0 0. So 1 and 0, and then you just compute those. And then you compute that, and you will get this kind of result. Not really that interesting. Still, it has a certain information. It's just about how the global Selmer group embedded into local Selmer groups, and then it actually measures that behavior. But I expect that if I use the elliptic curve or abelian varieties, then the BF, the Cassels-Tate pairing is not 0. And in that case, there will be a more interesting computation for entanglement entropy, but I'm not so sure how to do that. I think I'll stop here. Thank you.